Good announcement. התחלנו. מה נשמע? אוקיי, אז ככה. לי כבר יותר לך לדבר באנגלית, אבל לא משנה. Announcements. אחד, so I spent the weekend basically preparing notes about the precession because I was really troubled by the fact that nobody taught you precession properly. Classical mechanics precession. There's no point discussing GR precession if we don't speak, if you don't understand what, you don't know what is classical mechanics precession. So it's here, and I asked Akshay to deliver it to you. So there will be a tutorial today. It ended up to be lengthier than I thought. I think that the basic concept to understand is not hard. To do all the math, it can get a little more tricky. Especially when you make a separation between there is what's called free precession, and there is a precession caused by there is a torque, like סביבוני. תנועת סביבון. זה קיים גם על כדור הארץ, פוטנציאל לדעתי של השמש. So there will be a tutorial today. It will be after the lecture, the usual. So 10 to 12 will be a lecture, and then 1 hour tutorial by Akshay about precession. בסדר?
כך.
למה?
לדעתי שהתירו, אז קבעתי משהו.
לא ביקשנו.
משהו. צריכים להודיע למזכירות שיהיה, היינו צריכים להודיע למזכירות שיהיה, והם היו בקטע עכשיו.
טוב, האמת היא שזה גם, אני לא יודעת אם יהיה לי זמן להכין את זה. באמת ישבתי כל הסוף שבוע, כשהיה יכול להעיד, אני כמו ב-12 בלילה, אמרתי לו את הדפים. אני גם אשים אותם באתר הבית שלי, יש פה... האמת היא שלא בטוח שזה ייגמר בשיעור אחד, יש פה יותר חומר. אמרתי, כשהתחלתי לעשות את זה מסודר, אז יצא לי קצת יותר ארוך במה שתכנן. בכל מקרה אני אשים את זה גם באתר הבית, אבל זה יהיה תרגול, זה יכול לשנות את השנה. אמרנו שזה שומרים את השעה הזאת, לא רוצה תרגול נוסף. אוקיי, אז זה הודעה אחת, so tutorial. today, 12.1 about precession. The other thing, just a general note. אני ראיתי שיש פה חבר'ה שנכנסים לאתר הבית שלי ומסתכלים שם, יש שם סיכומי הרצאות ישנים שלי, וזה מצוין. כמו שאתם רואים, ההרצאות לא משתנות בהרבה, כי החומר לא השתנה כל כך הרבה מאז פעם קודמת. אבל, א', יש כל מיני טייפואים שאני מוצא ומתקן, וגם יש דברים קצת יותר רציניים, כמו כל מיני הסברים שאני חושב שאני מגלה מחשבה לדיעבד שאני לא הסברתי לכתוב, אז אני פשוט משנה אותם. זה היתרון בזה שזה סיכומי הרצאות שלי, אני עושה איתם מה שבא לי. סיכומי הרצאות שנמצאים באתר של הקורס הם מעודכנים. אז כל מיני טייפואים וכאלה, עכשיו אני לא יכול לשים אותם אחרי שאנחנו עושים. תדעו את זה, תהיו מודעים לדברים האלה. שוב, זה מצוין, אני שמתי אותם באתר הבית שלי, כי אני רוצה שאנשים ייכנסו וילמדו, וזה מצוין, אבל שימו לב שזה לא מעודכן. אם תסתכלו טוב, אתם תראו שבכל סיכומי הרצאות תמיד מופיע בהתחלה תאריך, תמיד. אז אם יש הבדל, גם של יום אחד, זה יכול להיות בגלל שמצאתי שם משהו. אז זה ההערה הכללית השנייה. ולמה אני אומר את זה? כי אני חושב בהרצאה האחרונה ביום חמישי, שדיברנו על הפיתוח של פרופ היו שם כמה דברים שאני לא הסברתי אותם מספיק טוב, אז אני שיניתי שם את ההסברים. נעבור עליהם ככה בקצרה עכשיו, כי זה דברים שכבר בעצם הבנו אותם, אבל יותר ביטחון אני לא אוהב להשאיר חורים לבנים כאלה בהסבר. בסדר, ואז אנחנו נמשיך בקוסמולוגיה. שאלות? הערות, טענות? טוב, אז בואו ככה בקצרה על הדברים שזה. עכשיו, חוץ מזה נראה שאנחנו מתקדמים דווקא בסדר גמור מבחינת החומר, שזה טוב, אני חשבתי שבגלל שזה סמסטר קצר לא נספיק. מה שאומר שיש מצב שנספיק לעשות איזה שיעור או שניים על גלית בידה. זה יהיה בשבוע הבא, אבל זה תלוי קודם כל אנחנו נסיים קוסמולוגיה. נראה כמה זמן נשאר לנו, ובהתאם לזה. בסדר? טוב, אז קוסמולוגיה. אז ביום חמישי עשינו את הפיתוח של מודל הקוסמולוגי. בעצם מה שנראיתי זה מטריקת רוברטסון ווקר. בדרך לפיתוח, נקרא, זה רוברטסון ווקר מטריקה. אמרנו, העיקרון הקוסמולוגי אומר שהמטריקה שלנו היא איזוטרופית והומוגנית, ואיזוטרופית והומוגנית בעצם אומר מקסימלי סימטריק ספייס. מקסימלי סימטריק ספייס. מבחינה מתמטית זה אומר שיש לו את המקסימום נאמבר של קילינג וקטורס. ופה זה נבע בעצם כל הפיתוח של איך נראה זה, איך נראית המטריקה. כשאמרתי בסוף, אבל זה כרגע פחות רלוונטי לפיתוח, כשאני אומר מקסימלי סימטרית, בעצם אני רק מתכוון לחלק המרחבי של המטריקה, לא לחלק הזמני, כי אנחנו יודעים שמטריקה משתנה בזמן. בין גילה ובעצם. עכשיו אמרנו שב-n dimensional, maximally symmetric number of killing vectors in ND is n plus 1 over 2. זה בסדר. עכשיו התחלתי לפתח את זה על ידי זה שהסתכלתי על התכונות של הרימן טנזור, בנוסף לתכונות של הקילינג וקטור. הגעתי למשוואה שנראתה ככה. מינוס r למדה רו סיגמה ניו דלטה קאפה ניו ועוד r למדה ניו סיגמה ניו דלטה קאפה רו מינוס r למדה סיגמה רו ניו דלטה קאפה ניו ועוד r למדה ניו רו ניו דלטה קאפה סיגמה k למדה קאפה שווה ל-r למדה סיגמה רו ניו ניו עוד r למדה ניו רו ניו סיגמה k
בסדר? האחרון באגף שמאל, הלמדה נראה קצת מעל האינדקס, כאילו זה לא, אין לראות החברה האחרון את שמאל.
בסדר. בעצם זה שיערת, מובן שאתה מבין את הרעיון הבסיסי, בסדר. אוקיי, ועכשיו אמרתי כזה, אמרתי את הטענה הבאה. זו הטענה שאני חושב שאני לא הסברתי את מה שצריך. אמרנו עכשיו, זה אמרנו משהו שהוא כללי לגמרי, שקיבלנו אותו עבור מהתכונות של הרימן טנזור ומהקילינג וקטור. אגב, אם אתם, זה אגב גם מראה שברגע שיש לי את קילינג וקטור, את הנגזרת הראשונה שלו, אני יכול לקבל את כל שאר הנגזרות. שימוש חוזר. עכשיו, הטענה הייתה כזאת. המרחב הוא מקסימלי סימטרי, ולכן בפרט הוא הומוגני ואיזוטרופי. הומוגני זאת אומרת שיש לי קילינג וקטור שלוקח אותי מכל נקודה לכל נקודה. נכון? שבנקודה מסוימת x, פחות רלוונטי, אני יכול לרשום אותו בתור דלטה. זאת אומרת, יש לי n ספייס, יש לי n killing vectors associated with translations. ובנוסף יש לי n מינוס 1 חלקי 2 killing vectors associated with rotations. עכשיו, מה זה קילינג וקטור ש-associated with rotation? מה זה אומר? הצורה שלו תהיה ש-K למדה בנקודה X שווה ל-0, בנקודה ספציפית, כן, אני נעשה רוטיישן, K למדה רו זה מינוס K רו למדה, גם בנקודה X. אתם לא רואים את זה ישר, פשוט תקחו את הנגזרת. יכול לרשום את זה K למדה רו, אחרת לרשום את זה K למדה רו, יש לי n צירים, nm, ש-m הולך, n זה מ-1 עד n, ו-m זה מ-1 עד n בעצם. נכון, אז יש לי n צירים, אני יכול לרשום את זה בתור דלטה למדה n, דלטה רו m, או דלטה רו n, דלטה למדה n. בעצם סיבוב. לא רואים את זה, תחשבו על סיבוב סביב ציר x נניח, נקבל שם y מינוס z או y. עכשיו, כשאני מציב את זה כאן, את זה אני מציב פה. הטעות שלי הייתה שלא אמרתי שזה עבור הקילינג וקטור הספציפיים האלה. כשאני מציב את זה פה, אז K למדה שווה ל-0, זה מתאפס, ואני נשאר עם המשוואה הזאת, שווה ל-0. עכשיו, את המשוואה הזאת אני יכול להביא לצורה יותר פשוטה, ומסתבר שיש דרך יותר פשוטה ממה שאני חשבתי, מה שנראיתי לכם בשבוע שעבר. הדרך היותר פשוטה היא להסתכל על שני האיברים האחרונים בלבד, שני אלה, ולרשום אותם בצורה הבאה. מינוס R למדה סיגמה רו ניו דלטה קאפה ניו ועוד R למדה ניו רו ניו דלטה קאפה סיגמה K למדה קאפה. אני משתמש במשוואת קילינג, אז זה שווה למינוס R למדה סיגמה רו ניו דלטה קאפה ניו ועוד R למדה ניו רו ניו דלטה קאפה סיגמה K קאפה למדה.
אבל נכון אתה מחליף את התמונה של דם אינדקסים.
מה?
ואז אתה מחליף את
בדיוק, ואז אני מחליף את האינדקסים. עכשיו מינוס מינוס פה זה פלוס הופך להיות, וזה הופך להיות מינוס. עכשיו מותר לי להחליף את האינדקסים, כי זה דם אינדקסס, ולכן זה שווה ל-R קאפה סיגמה רו ניו דלטה למדה ניו פחות R קאפה ניו רו ניו דלטה למדה סיגמה K למדה. עכשיו אני מציב את זה במקום שני אלה, זה שווה ל-0, K למדה קאפה לא יכול להיות שווה ל-0, מה שאומר שכאן מה שיש לי בתוך הסוגריים צריך להיות שווה ל-0. ולכן נקבל פה שמינוס R למדה רו סיגמה ניו דלטה קאפה ניו ועוד R למדה ניו סיגמה ניו דלטה קאפה רו ועוד R קאפה סיגמה רו ניו דלטה למדה ניו פחות R קאפה ניו רו ניו דלטה למדה סיגמה שווה ל-0. אז ההמשך היה פשוט לעשות את הקונטרקציה של קאפה ומיו. קאפה ומיו. נכפיל ב-G למדה אלפא, ואנחנו נקבל מה שפיתחנו, n פחות 1, R סיגמה רו, אלפא רו סיגמה ניו שווה ל-R ניו רו G אלפא סיגמה פחות R סיגמה רו G אלפא. בהמשך כמו שעשינו בסדר? אני כאלה שמחים. כן.
יכול להיות שיש לי blackout, אבל יש לי תחושה שאת המשוואה K למדה X שאני רואה כאן, יש כאן וקטור.
יש לי קילינג וקטור.
קילינג וקטור.
associated עם rotations. מה זה associated with rotations? זה אומר שאני לוקח, יש לי פה מרחב, יכול להיות גם דו-ממדי, לא אכפת לי, ואני מסובב אותו. סובבתי אותו סביב הנקודה X. מה זה אומר?
זה אחת הנקודות?
כן, X זאת אחת הנקודות. מה זה אומר שסובבתי אותו? זה אומר שנקודה X לקחתי אותו לעצמי.
אני איתך. אז יש פה איזושהי בעיה, כי לי קל היה לקרוא ש-K למדה X לכל X שווה 0, כאילו זה...
אני תמיד יכול למצוא, עבור כל X אני יכול למצוא כזה. אבל אני דיברתי ספציפית על K למדה בנקודה X מסוים.
כי אתה מדבר על סיבוב סביב הנקודה X.
נכון.
בסדר. אני חושב שזה חסר בהסבר, כי גם בשיעור שעבר וגם עכשיו זה בלבל אותי לחלוטין.
טוב, אז אני שמח שעכשיו העסק הזה הוכח. בסדר? ומפה אני ממשיך הלאה, כמו שהבטחנו, ובסופו של דבר אני קיבלתי את התוצאה שאני רציתי, שזה שעבור מרחב בעל סימטריה מקסימלית, אני יכול תמיד לרשום את הרימן טנזור בתור למדה או סיגמה נו שווה לך K איזשהו קבוע כלשהו שאני לא יודע מהו G או G למדה סיגמה פחות G סיגמה או G למדה שבעצם אומר ושוב אפשר יחסית לראות את זה אינטואיטיבית, כן? מרחב עם סימטריה מקסימלית אומר שהקורבצ'ור שלו הוא קבוע. זה בעצם מה שזה אומר. עכשיו, כשרואים את התוצאה הסופית... למדה רו סיגמה. היי.
Speaking in Hebrew from the surface language, and there are 3 Chinese students.
Okay, sorry. Not here. Thanks for letting me know. Okay, and my apologies for those at home. You're expected to be here. So what it means is that in a space with a maximally symmetric space, then the curvature tensor really depends on, it's really constant everywhere in space. Which again makes perfect sense when you think of that, right? Because what is a maximally symmetric space? It's everywhere the same, doesn't matter where you look. And with that, we continued on to derive the Robertson-Walker metric, which we showed looked something like that. dn squared was a minus dt squared plus a squared of t dr squared over 1 minus k r squared plus r squared d omega squared. So there are 2 things here. One is we make the separation between the time and the space. Right? The space is multiplied by some function of the time. We allow this freedom. So there are 2 degrees of freedom here. One is this one function of the time, a of t, we'll see what it is today. The second is this k, constant k, which we don't know what it is. Okay, 2 degrees of freedom. Now we said...
do we have any constraint on a?
We will. For the time being, the way we derived it is just some function of time.
We don't really care for what k is, just sun, right?
Yes. Then we said, okay, the exact value of k is of no importance because we can always renormalize the coordinates, right? So if we renormalize k to k over the absolute value of k, and then r to square root of k, absolute value of kr, and then a to a over square root of k. then nothing really changes. You get exactly the same result. Right? You can just plug it in and you see that it's the same result. Yeah.
אבל כן אכפת לי, נגיד בהנחה ש-K הוא חיובי, אז ראינו שדרנו שהעולם הוא כמו כאילו כדור אם הוא סגור אז כן אכפת לי להשים כדור בארץ או כל הכדור.
That means that K can really, if we do that, that means that K can take only 3 values. -1, 0, and +1. Everything else we can really rescale into the coordinates.
Do we know actually what is the value?
Wait. Slowly, everything will be new to you. -1, 0, and +1. Right, so -1, they call it open, this we call flat, this we call closed. And that's it. These are all the options we have. Everything else doesn't really matter the exact value. And then we said, okay, actually maybe it looks a little bit complicated, but really there is nothing here. Because if we put K equal to 0, what we have here is just Euclidean space written in polar coordinates. So rather than dr squared, I'll call this d sigma squared. So d sigma squared, just dr squared plus r squared d omega squared, which is nothing but dx squared plus dy squared plus dz squared. So it's a flat space. Euclidean space, zero curvature. The other two are as simple, right? If we have a closed one, K is equal to +1, then we just change variables. R is equal to sine omega, which we call chi, and then d sigma squared is d chi squared plus sine squared chi d omega squared, which is a 3D ball. We're familiar with the 2D ball. This is the 3D ball, so we cannot really imagine it, but it's 3D. It's a ball.
3D sphere.
3D sphere. Well, it's a ball, but I mean, it's the only thing which is very difficult to imagine is the open, K equal to -1, in which case I write down R equals sine hyperbolicus of some function, called it psi, and that gives d sigma squared is d psi squared plus sine hyperbolicus squared psi d omega squared. That's the opposite sphere. Sphere is a negative curvature. Yes.
We can get drop the time dependence in the a squared t. If we still maintain that, the first line still be a flat space.
Yeah, of course. It's a flat space.
With changing scale.
It's minus d squared plus a squared times d sigma squared. Yeah. The coordinates.
There's the t dependence, right?
Yeah, there's t dependence. So that means that we have a flat space, and when time evolves,
so scales.
The coordinates can expand or shrink, depending on how the time changes. Like zoom in or zoom out, that depends on A. But the structure of the space is still flat. It's not changed.
Can we imagine what physically would happen to stars, matter, and so on in light?
With the stars, we will not have to imagine. We will actually calculate. Okay? Yes.
For a closed universe, R is bounded.
Sorry.
For a closed universe, R is bounded. Is it?
That's the meaning of closed. Yes.
It's problematic.
Why?
No.
Like a balloon.
Okay. That is something that people. That is an example that people give, which is wrong, conceptually wrong. I will explain to you either today or on next lecture Thursday. It is conceptually. I mean, it's something that often you hear that in lectures, and in textbooks and YouTube and whatever you're getting your information from, and it is good in explaining why the Hubble's law, why galaxies recede away from us, like they are, dots in the edge of the surface of a balloon, which is expanding. Conceptually, this is incorrect. We'll discuss it. Okay, so take it very, very carefully. Yeah, we're getting to exciting things, and then these things Okay, yes.
If we're okay with the universe expanding or not,
Well, we're not there yet.
can other things can vary with time, like other constants and things conceptually are constant? Could the gravitational
We are,
constant?
that is a matter of active research. Is the constants of nature really constants? Maybe a long time ago they were different than the way they are.
The other are different in different energies.
Right. That's right.
We know
Wait. Everything will be, let's do one step at a time. The answer is we do not have any evidence. Right? We do have questions which we don't know how to solve. But there is nothing that tells us that the constants of nature are not constants at the moment. Right? For now, focus on understanding what is written here. What is written here, all this derivation plus what I repeated now is just to show you that when we speak about the maximally symmetric space, in reality this is a maximally symmetric subspace or inner space, we only have 3 options. That's all. And the values of k can be only one of 3, -1, 0, 1, 0. That's all. Okay? And then intuitively it's quite easy to understand why Euclidean is called flat and there is no curvature, and why sphere is has a positive curvature. Okay? With me? Okay. Now, what we did not do yet.
So,
Yeah, we did not make any attempt of solving Einstein's equation. And so this is the next logical step, is to take this metric, which is derived here. Let me put it up there so I won't erase it. ds squared is minus dt squared plus a squared of t. dr squared over 1 minus kr squared plus r squared d omega squared. And use it in Einstein's equation. And
If the energy is just what's the value of this?
put it shortly. You can think of it already right now. The answer is going to be called
Zero.
Friedman equation.
It's not 0 because, well,
Of course
we
not.
have matter.
Of course, it's going to be 0 because the universe is not empty. So what do? Well, we have the metric. So from the metric, I'm just going to write down a dot dA over dt. That's what I'm going to use. So step number 1 is to calculate the left-hand side, which contains the Ricci tensor. So the way to do it, we just have to go through the long way, direct our hands. So the first thing to do is to calculate the Christoffels. So from the metric, given the metric G mu nu, when we calculate the Christoffels, gamma mu nu.
we already know what the metric is.
This is the metric.
Ah,
So the calculation
we
of
also know what the
Christoffels. Don't know what the Christoffels are. I just have to plug in the equation and
So
solve
that we when we calculate the Riemann tensor with the G, the maximally symmetric. Like if we just contract the Riemann tensor.
yeah, but this was just for that part. Now you need to do it for everything. Right? We just did it for the spatial part. Now, again, we do it for the entire metric, including the TT and A. So, that's why I just shortened the A over the T is A dot. And all the components, I just have to write it down now. Again, there is no short here, shorten. So, gamma 0, 1, 1 is A dot over 1 minus k r squared. Gamma 0, 2, 2 is A dot r squared. Gamma 0, 3, 3 is A dot r squared sine squared theta. Then gamma 1, 0, 1 is gamma 1, 1, 0 is gamma 2, 0, 2, which is gamma 2, 2, 0, which is gamma 3, 0, 3, which is gamma 3, 0, which is A dot over A. Gamma 1, 1, 1 is K R squared over 1 minus K R squared. Gamma 1, 2, 2 is a minus R, 1 minus K R squared. Gamma 1, 3, 3 is a minus R, 1 minus K R squared. Sine squared theta. Gamma 2, 1, 2 is a gamma 2, 2, 1, is a gamma 3, 1, 3, is a gamma 3, 1. It's 1 over R. And then gamma 2, 3, 3 is a minus sine theta. Cosine theta. Gamma 3, 2, 3 is a gamma 3, 3, 2. Is a gamma spontaneous. Okay. Plug in.
The rest of it.
What? The rest is 0. Of course. From that, calculate the Ricci tensor. And again, the only non-zero component of the Ricci tensor will be the following. R 0, 0 is a minus 3 A dot dot A. R1, 1 is A dot dot. Maybe, you know, I'll put it right here because I'm going to use it. Can you see when I write it? R 0, is minus 3 A dot dot A. R1, 1 is A dot dot plus 2 A dot squared plus 2K divided by 1 minus K R squared. R2, 2 is R squared, A dot dot plus 2 A dot squared plus 2K. R3, 3 is R squared, A dot dot plus 2 A dot squared plus 2K sine squared. Okay, that's what you get. And then from here, it's immediate to calculate the Ricci scalar. R 6 over A dot squared. A dot dot plus A dot squared plus K. That's pretty much straightforward. Again, it took Friedman, I guess, more than you today to do that. Today you can just plug it into one of your favorite Mathematica, whatever tool you have, and you'll get it. Okay, so this is from the left-hand side. What about the right-hand side? Now we have the matter content of the universe. Of course, as we said, the universe is not empty, so we cannot assume it's T0, T mu is 0. Are you still copying, or can you erase that? What did we say about the universe that it's made of? Right. Other words? Perfect fluid. Very good. So the universe is made of perfect fluids. And what do we know about perfect fluids? Specifically, we can say that they are isotropic in the rest frame. Right? They are perfect fluids, so the universe is made
what's the rest frame?
of perfect fluid. A second. Fluid. Therefore, we can write down T mu nu is a rho plus P. U mu plus P G mu. Just a reminder, rho is the energy density. Includes the mc squared, P is the pressure. I don't know if you ever thought of that. Pressure has units of energy density.
Oh, this is general definition.
That's a perfect fluid, and these are measured in the rest frame.
But what's the rest frame?
Just a second. Just a second. Now for your question. Maybe I should erase it now. Just a bit for a second. Now the point is the following. In the fluid rest frame, fluid is isotropic and the metric is isotropic. Right? So what does it mean? Fluid here is isotropic. Yeah, metric is isotropic, right? So that means that the two frames has to be the same. If the fluid, isotropic fluid in a frame leads to a metric that is isotropic, then two frames have to coincide. So in that frame, which is essentially the rest frame of the fluid, write down u mu is 1, 0, 0, 0. This is the rest frame of the fluid. Essentially what I'm saying is that the fluid is isotropic in the co-moving frame.
Co-moving is moving with the universe.
Yes.
So it is moving.
Co-moving.
Co-moving with the universe.
So relative to the fluid, the universe is not. In which case, I can write down T mu nu. Sorry, because it's lower coordinates. Just to be 0 for less. T mu nu is just rho 0, 0, 0, 0, 0, 0, and then P G I G. Yeah.
So if the fluid is stretching with the universe in order to stay moving,
You're confusing too much. I'm just saying, in the co-moving frame, like everything is homogeneous and isotropic, and the fluid is homogeneous and isotropic. So everywhere you look, you're seeing the same number of galaxies on the average per unit volume. That's all. You don't have a concentration of galaxies at a certain location. That's all there is. Okay. If I raise one index, T mu nu, right, I have G I J G I J, so just give me a 1, so I get the diagonal of minus rho E. I just want to put it here, which means the T, which is T mu nu, is what? Minus rho plus 3. Just the sum. Now that I'm going to put in Einstein's equation. So let's put that in Einstein's equation. So Einstein's equation. R mu nu is 8 pi g. T mu nu minus 1/2 G mu nu T. Just slightly change the notation, but leave it to that. So the 0, 0 term, mu nu is equal to 0, 0. Zero zero R 0, 0 is a minus 3 A dot dot A. Is equal to 8 pi g T 0, 0, which is a rho, minus 1/2 G00, which is a -1. So it's a plus 1/2. And T, which is minus rho plus. Yeah, I just like it. G, I know what it is. We have the metric. R, I calculated. T, I calculated. Straightforward. Or minus 3A dot dot over A. This is 1/2. So I can write it down as four pi G rho plus 3. That's one equation. Then I have what?
What we know about the pressure density?
Wait, we don't know yet. I'm writing down a general equation. We haven't finished. This is just a 0,0 term. Now let's look at the ij term. Nu is equal to ij. So Rij is equal to 8 pi g. Here I have Gijp minus 1/2 Gij minus rho plus 3p. Let's copy it from here. So this is 8 pi g. One half Gij rho minus 1/2 minus 3/2 plus 1 minus 1/2 Gij p. So 4 pi g Gij rho minus p. How many equations are written here? 9. But is it really 9? Why not? And it's isotropic. Everything is isotropic. Right? So only one really matters. If I know one, I know them all. Right? I know 1, 1, 2, 2, 3, 3. They have to be exactly the same. Right? So I can choose, for example, here. Choose Ij equal to 1, 1. I have R1, 1 from there. It's going to be A dot dot plus 2A dot squared plus 2K over 1 minus KR squared is equal to, what is G11? This is G11.
A squared over 1.
A squared over 1 minus KR squared times 4 pi G rho minus B. That goes down and we're left with A dot dot over A plus 2A dot over A squared plus 2K over A squared is equal to 4 pi G rho minus B. Okay, now we have A dot dot over A, so we can use that equation, right, to remove the A dot dot over A here. Because this will be written as A dot dot over A is a minus 4 pi G over 3 rho plus 3p. plug it in here. Many terms will cancel out here because I have minus 4 pi g p minus 4 pi g p, that will cancel out. So what we're left with is a dot over a squared is 8 pi g over 3 rho minus k over a squared. That's a basic algebra which interests me not. These two equations, these are non-spherical equations. And when we have a metric, this is the Robertson-Walker metric. What these equations really tell us is the evolution of the scale factor, A of t, right? Which, as we see, depends on rho, on p, and on k. Right? Rho p, energy density and the pressure of the universe, assuming it is completely homogeneous. K is the curvature, which we don't know, but we have three options. Okay. Together with this metric, so these three equations together, or this metric with A that obeys Friedman equation is known as Friedman-Robertson-Walker metric, or FRW universe. Yeah? Okay. Questions? Derivative should be straightforward. There was not too many things to do. Everything we just used the same prescription and we just plug it in. Now let's look at the result. Yeah, I did not put yet the cosmological constant. I will add it up. It's not here yet. You'll see when I want to add it. Global properties of the universe. So, first thing we're going to do to explore the global properties is to define a few parameters. Remember, we don't know what is the scale factor. It's still unknown. We don't really have a way of measuring it because we don't know what is the coordinate. We don't know what is r. But we can define the rate of change, a dot over a. And do you know how we call this a dot over a? It's not constant. Nothing constant here. Right, so it's called the Hubble parameter. H is defined as a dot over a. And what units does it have? What? What units? Essentially 1 over time. Yes. Right. This is something which we can measure, or hope to measure. Now we define a second parameter, which is known as the deceleration parameter. Is acceleration parameter. U is minus a dot dot over a dot squared. This is the rate of change of the rate of expansion. Now, just historical moment, right? Hubble had two great discoveries. What was the first great discovery that he had? Sorry, no, that was the second one. Until Hubble's time, everybody was sure that the Milky Way is the entire universe. All the stars are here, around here, in general vicinity, right? Hubble was the first to discover what there was things which was called nebula, right? Some objects which did not look like star, but some foggy things. He was the first to realize that the foggy thing, which is known as Andromeda, is really a galaxy like our own. It's very far away from all the other stars. How did he do that, by the way?
Telescope.
There were telescopes before him. How did he realize it was far away? It's too far to any parallax. What? I don't know. Right? That goes back to a woman which is called Henrietta Leavitt, which you might have heard. She was looking at, there are some stars that change their brightness. So it's like pulsating stars, it's called Cepheids. And she discovered that there is a relation. It was very clever, and she was very, very clever to discover the relation between the period and luminosity, right? So, more luminous stars have a longer period, brightness, right? Time and brightness, intensity. Right? The smaller ones will have a shorter. Right? This was Henrietta Leavitt. The times where women in astronomy were not really taken too seriously, but she was one of the pioneers. Then Hubble, what he did was discover these Cepheid stars in Andromeda and understanding these were Cepheid stars. Therefore, he could understand that he knew what is the brightness, he knew what is the brightness of the stars, so he knew he could measure the distance. We'll discuss that further when we talk about how to measure distances, which is one of the greatest problems in astronomy in general. You're seeing some light, how do you know how far it is coming from? How far is the source from us? It was first Hubble's great discovery. Understanding that the universe is not limited to our own galaxy. It extends beyond that, discovering that there are galaxies around. And the second great discovery was, of course, Hubble's law, which we will derive, which is that the galaxies recede away from us. By the way, Andromeda galaxy is not, the others do. Okay. So Hubble's parameter, it's clearly is time dependent. It changes with time. How do we call Hubble's parameter today? So H0, when we put a 0 in cosmology, that means today. Okay. H0 is simply Hubble's parameter, A dot over A at T0. Be equal to T0, which is today. This is known as Hubble's constant. Although there is nothing constant.
What is its value?
What?
What is its value?
It's a good question. The value which is sufficient for you to know is 70 plus minus 3 kilometers per second per megaparsec. Right?
It's not how is it units hertz?
What?
How is it the units hertz?
One megaparsec is a astronomical unit distance, right? How much is a parsec? 3 times 10 to the 18 centimeters. Normally it's almost 14 centimeters. So megaparsec is a million times, 3 times 10 to the 24 centimeters. Plus minus 3. Actually, this is not exact, right? But now the situation, like, why? That's a measurement we have. This is something which we measure. Now, this is not exact. The most accurate, reliable measurement that I know of is by the WMAP satellite, which published in 2018. So the exact value is 67.66 plus minus 0.42 kilometers per second. Now, why am I saying this is most exact value? Now, you might have heard a thing that is called Hubble's tension. Have you heard that? This is something which is kind of quiet and scientific news in the last 5 years, basically. Today there are several ways of measuring. I just mentioned it. I'm not going to go deeper into that unless you really insist. So this is the exact. Again, I say exact, but some colleagues may not agree with me that this is the exact value. The thing is the following: there are various ways of measuring Hubble's constant. Okay? It's not constant, but there are various ways of measuring it, and there are direct ways and indirect ways. Okay? Direct ways normally associated with the local universe, how the galaxies in the local universe proceed away from us. Indirect measurements rely on looking very far into the past, and specifically at the cosmic microwave background, from which you can deduce various information, including the value of the Hubble's constant. And in recent years, there seems to be a discrepancy of the order of 5 sigmas. So the more distant ones are somewhat lower, more distant measurements, and it's around 67 point something, 67, 68, depends on who you claim. The more closer in one, measurement based on the local universe are higher, something around 73-ish. But it's about 5 sigma away, and this seems to be problematic, and people don't really understand why is that. Now, most likely result is that there is something in the methodology, maybe in the calibration, something is being done wrong. Of course, the teams that make the measurement do everything they can to avoid measurement errors of various types, but things can happen. There are several groups that measure each one, and each one they are consistent with each other when it goes to the distant past measurements and to the nearby universe measurements. And nobody really understands the origin of that. Of course, one possibility is that there is something basic in the physics that we don't understand. That goes back to the question I was asked about changing of physical parameters, physical constants this time. But I will say this is the most extreme possibility. A more likely possibility is that there is something wrong with the methodology of the measurement of something. Yes? No, it's H0 today. Right? It's measurement of H0, not of age. Age changes with time. You can look at this and past. Maybe I'll talk about that. Depends how much time I'm going to have. Right? I could talk how we make measurements. That makes gets into more technicalities. Which are אנחנו מדברים על מיליארדים של שנים.
לא, הפער המדידות הוא לא נובע מזה שהוא ההאבל משתנה.
No, Hubble's constant is supposed to be constant. It's not supposed to change. We'll discuss it. It's not supposed to change today. In the past, of course, it did change. And it's not changing. The past means not million years ago. We'll see that. We'll discuss. What do I mean by the past? Okay. So, yeah.
How this allows the text? It won't be extensions, but shrink.
Wait. Everything. One step at a time. Okay. For us, for the purpose of this course, this is introductory course to give you the basic ideas of how these things work. This value is sufficient. Now we're going to see in a minute why exact measurements are so important and why people are doing it. So, well, let's do it right now, actually. So, this is Hubble's parameter. So I can take this equation and write it down in the following way. 1 is equal 8 pi g over 3 h squared rho minus k over a squared h squared. And that I can define critical density. rho critical as 3h squared over 8 pi g. And again, we can measure that. So today we can measure that if we know Hubble's constant today. G is fixed, assuming, so rho critical today, 3h0 squared over 8 pi g is 9.21 times 10 to the 130 gram per centimeter cube, or more reasonable units is energy, electron volt, 5.19 times 10 to the 3 electron volt per centimeter. That's a critical density. Then it's the same value, just a change of.
לא, הכוונה היא שכאילו, בצפיפות הזאת אנחנו שכוח, מעל זה.
So you already see what happens here. Now, we further define what is known as the density parameter. So the density parameter, omega, is 8 pi g over 3h squared rho, which today is rho over rho. So this equation now can be written as omega minus 1 is equal to k over h squared a squared. Now you see what happens here. Let me remove that a little bit more. So, if rho is smaller than the critical, the energy density in the universe is less than the critical value. What does it mean? Omega is smaller than 1. What does it mean? Okay, it must be minus 1. This is always positive h squared a squared. Which means that the universe is open. If rho is equal to the critical value, then omega is 1, okay, is equal to 0, and the universe is flat. So you see why it's important to measure this. People spend billions of dollars / euros. Rho is greater than rho critical. Omega is greater than 1, and k is equal to +1, and the universe is flat.
What's physically does matter if the universe is open?
What?
How physically does it matter if the universe is open, closed, or flat?
How physically?
Does it matter if the universe is open, flat, or closed?
What do you mean does it matter? For your daily life here, it's
not for my
likely
daily life. Physical predictions.
Yes, it does have give physical predictions, which we're going to discuss one step at a time. I promise you, everything will be clear. Of course, it does have physical predictions. Everything has physical predictions. So if we measure, right, if we know the density, sorry, you don't need to know the density. You just need to know, yeah, you don't need to know the density. If we know the density, then we know what is the fate of the universe. Does any of you have any idea what is the measured value of omega?
It is 1 plus minus a very small thing.
So measured, omega is 1.0023 plus minus 0.005. What is it? Nothing in this theory tells us what the value of omega should be. Right? The equations we derived, they are completely general. We did not specify what value of the Hubble's parameter, what value of the density the universe should have. It just happens to measure it. Derived all this theory, right? All these equations, essentially this equation, and then we went on and looked. Right? And when we measured, this is what is being measured. Which means that as of today, we do not know whether the density is subcritical, supercritical, or exactly critical, and so we don't know if the universe we live in is open, flat, or closed. One thing which we do know, this is quite important, that omega is very close to unity. Again, it could be anything. It could be 27. It could be 0.10 to the minus 15. It can be any value. Yet it's very close to unity. As far as we can tell, it's consistent. It's definitely consistent with unity. Why is that? In physics, any value that would be here, people would ask why is that? But this is a specific value which we happen to have. In physics, we don't like fine-tuning. Right? We don't like something which is not clearly understood. This is one of the origins of the theory which is called inflation, which is supposed to explain several things, and this is one of them. Right? Again, if you want, you can discuss that, but then it will be either that or talking about gravitational waves. Inflation typically is being taught in the more advanced courses. Or in cosmology. There will be a special course in cosmology, then we can talk about inflation. Okay? That's one of the motivations. Interesting. Yes, no, maybe? Questions? Yes.
We hang everything on a mysterious function called A and measure something called Hubble parameter.
Right.
Could we normalize A to be 1 and not changing it? Put all the blame on G, saying that G is not a constant, it's a function of time.
A we define as something that changes with time.
Yeah.
When we wrote down Einstein's equation, we specifically assumed that G is constant. Now you're asking, okay, now I want to go what's called beyond Einstein's theory, or somebody mentioned it already. Assume that the constants of nature are not constants, and see where this is heading, what this gives us. You can be, but again,
No,
there will be other consequences for it, which are more problematic. For example, if you say G changes with time, then that will affect the evolution of the early universe, of the galaxies in the early universe, of the cosmic microwave background. There are a lot of indications. I will discuss them at the end. By the way, if you look at my lectures, they are not in my lectures. So there are many, because I just didn't put them. There are many indications that says that what we do here is correct. Just looking at the cosmic microwave background and its fluctuations, you get a huge amount of information which will give you huge constraints of many of these parameters. So if you want to say, okay, I want to play with G, and I said G is not the same today as it was in the past, we have to see how that coincides with what we're seeing in the past. Specifically, cosmic microwave background. Also, it's not just that, it's the number of not the number. It's the fraction of elements that we have, hydrogen versus helium in the stars, because that will affect the evolution of stars.
So while G is appearing here alongside with H0, there will be equations where G is not affected, it is not connected to H.
No,
It is
there will be no. This is just happens to be here, right? But you saw G in other places. This is just, look, I just derived this specific equation, which is directly related from Hubble's, from Friedman's equation, which was derived from Einstein's equation.
Where is G appearing in other places?
Again, we'll discuss a little bit the cosmology. If you want, we can extend it. I can have a full lecture on that. I have it already ready, which I gave a few years ago. That's not the problem. The question is, well, there is a compensation. We don't have that many lectures now. I'll mention that cosmic microwave background towards the end, and maybe I'll extend a little discussion about it. So, yeah, question.
If you're changing k is very small, like it's over 1, but it's close to 1, how is it much different from the flat?
We said we don't really care what is the value of k. K can be positive, 0, or negative. We can take any value, but we can always normalize the coordinates. So there is a conceptual difference between k equal +1 and 0 and -1. But there is no difference if k is equal to 2 or 3 or 500. Right? We just normalize, we just rescale it with the coordinates to 1. That's all. Yeah.
The density can change with time. And you said that k
That's what we're going to discuss
not
now.
changing. So it means that if we're above critical density, the density can never decrease below critical density, or else the universe will.
Yes. In a sense, it makes sense. You'll see that. You'll see that maybe not today, but next lecture, Thursday, things will be clear. Promise. Because now, actually, this is the next subject. Some have this tendency of running just to the next subject. The brain thinks fast, which is good, but clear that, and then we move on to the next subject. Okay. Got the idea. Again, what I want to emphasize, that's a theoretical. That's a measure. Nothing in the theory tells us what the value of omega should be. Right? Theory just tells us if omega is that, that's what. If omega is that, that's what. It so happened that this is what we measure. We don't know why it is so. When I say we don't know, there is no consensus. Some people say, "Oh, I have a great theory that explains that." Other people say, "I don't believe in hard sources." Right? Okay, move on. Now I was asked, okay, so what is this rho and p? And the question, and the answer to that question is that depends. Depends on what? On what we have in the universe. So what are these rho and p? Sorry? Content of the universe. So we have the stress energy tensor. Conservation of energy. It's always true. Zero is double mu T U 0. The 0 is conformal. T mu 0 plus gamma mu 0. T00 plus minus gamma lambda mu 0 T mu lambda. This conservation of energy. What is written here? What is T? The 0 here. T0 and T0, so that's going to be a minus T0 rho. And here now I have to go back to what was written on the board, and I erased it. T00 is of course rho. T mu lambda will just be P if lambda is equal to mu. So overall I get a minus 3A dot over A rho plus mu. By the way, somebody asked me, it's not a good place to stop and marking. Right? Somebody asked me about the conservation of energy, right, in the stress energy tensor. Right? When I write down the stress energy tensor contains not only the energy density, right, but the flux of energy. Right? This is the non-zero terms. T00 is the energy density, T0I are the flux of energies. Right? So when I write conservation of energy like that, it's essentially equal to saying, okay, I look at the energy density, and it can change in time. If there is a flux coming in, it will grow. If there is a flux of energy going out, it will get down. Okay? Everything is contained within this equation. That's why it's a tensor. It's not just a scalar. So ignore that for a second, and you or more than a second. That's a conservation of energy. That's not still enough to tell us too much about the gas and too much about the evolution of the scale factor, which is what we're up to. What do we need more to specify the gas?
Relation between rho and P.
Yeah, it's a relation between rho and P, the energy density and the pressure. How do we call such a relation? What? Equation of state. Equation of state, right? So we have to add plus add equation of state. That which is a relationship connects rho. Now, of course, equation of state depends on the gas we have. Different gas will have different equations. It turns out that for everything that is relevant in the universe, equations of state have a very simple form, which is P is equal to omega rho. General equation of state. I'm going to show it to you in a second. Right now, just accept that. And rho and omega is some constant. Time independent. So if I pull that, I have rho dot is equal to minus 3 A dot over A, 1 plus omega rho. So rho dot over rho is equal to minus 3 A dot over A, 1 plus omega, which the integrating that is pretty straightforward. You just get that rho is proportional to A to the power of minus 3, 1 plus omega. So again, this tells us, if we know what is the equation of state, how the energy density, also how the pressure change with the scale factor, which by itself depends on the time. So how the energy density of the universe changes with time. Okay. So what do we have in the universe? How many options do we have? What?
Less than 0.
No, now I'm talking about the matter. I want to now solve that. What is in the universe? What is the universe made?
Stars.
Stars, right? Okay. How do we call stars another way?
Gas.
What? Gas, right? It's the same. How do we call it? What?
Ideal gas.
What?
Ideal gas.
Ideal gas, yeah. What? Yeah, that's
Also
dust. Dust. Right. So that's all I want to call. What is a dust? We said it already. What is a dust? What is a dust?
It's a point particle.
With what?
Degrees of freedom are just the momentum.
What is the characteristics of a dust? What is the pressure of a dust? Zero, right? It's just a bunch of particles that don't exert any pressure on each other. Right? Just lying there and just wipe them from the floor, or from the air, or whatever, right? So they don't put any pressure, right? In that sense, stars are dust, right? They don't put pressure on other stars. Right? Galaxies are dust, so we call this matter. So dust. So
Why does it have it?
you don't have pressure. You don't put pressure on others. Not about gravity. We're talking about pressure. We're talking about no pressure, right? We can think of it as a bunch of particles, a bunch of stars. They don't put pressure on each other, right? They don't push them away. So matter of the universe, or content of the universe. So one is called dust.
Dust.
We call it also matter. And what did we say about dust? What is the pressure of the dust? Zero. So what is omega?
In that sense, what is the pressure of the air? Also zero?
Yes.
The air molecules give zero pressure.
No, I have to be careful because there is a lot of interactions between them.
Also
stars
stars
are
are galaxies.
No, because they interact with each other. But galaxies far away do not.
But the interaction is just colliding and transfer momentum, or almost.
Yes.
The
But
stars
here-
do not collide.
No. Galaxies. You can look at different galaxies. They will not collide with each other. Or it's so rare that you can do that.
It's just a matter of time scale.
Yes. Matter of time. So about the universe, we've seen the time scale, the age of the universe, which is what we care about, right? We can assume it's a zero question. Now, if you say this is not exact, yes, I agree, it's not exact. There is something in there, yes, there is something. Zero's order approximation, that's all. Omega is equal to zero, so what does it mean? About the evolution of the density. Rho matter goes as A minus 3. Which again makes perfect sense, right? What is A?
The volume.
Yeah, right. A is the scale factor, right, which multiplies all the coordinates. Right, so if I have, right, this is the coordinates. Let's say I put one particle within a volume element. Now after some time, the coordinates are multiplied by A. Right, this is dr, this is A times dr. The dust is still there. Right, so the density or the energy density drops as 8 to the minus 3. Right? It's kind of straightforward. So if most of the content of the universe is made of matter, this is called a matter-dominated universe. Makes sense. And in a matter-dominated universe, the density of matter will drop as the energy density and the density of matter. Why?
Non-relativistic.
Yes, non-relativistic. Right? Why energy density and density are the same? Because most of the energy is in the rest mass, mc squared. Like thermal motion is much less than mc squared. This is called matter dominant. That's one option. Now we have a second option. What is that? Radiation. Now for radiation, so this is one. That also contains relativistic particles, so particles for which I cannot ignore the kinetic energy relative to the rest mass energy. Okay. So it's either electromagnetic radiation or relativistic matter. What's the pressure? What's the equation of state for relativistic matter or for radiation?
Is proportional.
Okay. So there's more than one way to derive it. So we can start from the, you know, do various derivations. So the relation between P and rho, we can write E is equal to P times C. Right? P is the momentum. Okay. So the pressure by n molecules, consider n molecules. Right? The pressure inside the box. It's just easy to see with it. Right? You have a box. The molecules, they got in, put pressure on the surface, right? There are many like that. So what is the pressure? 1/3 n over V. Say that in first year or in thermodynamics course.
Second year.
Second year, ever seen that. But P dot V, V is C, right? Because it's relativistic, so it's just 1/3 n over V and E. What is n over V times E? Rho is the energy density, so it's rho over 3. Right. Now, if I want to be a little bit more sophisticated, did Akshay or anybody showed you the stress energy tensor of the electromagnetic field? No? T mu nu is 1/4 pi.
This is
F mu lambda F nu lambda minus 1/4 G mu nu F lambda sigma F lambda sigma. Did you see that? Did any of you see that? Well, this is news for you. What? We skipped that point. Okay, so you can write an energy momentum tensor not only for matter as we wrote, you can also write it for electromagnetic fields. That's how it looks like. And if you do it, you get this result right away. But since you didn't see that, I'm not going to start doing it now. Anyway, what is this, by the way, you're supposed to learn. You're supposed to learn it in the classical fields, second or third year fields. Mashkin. Faraday tensor, stress energy tensor is something that you're supposed to learn.
גם בסדר, לא בטוח נגיע לזה.
לא תגיעו כזה, בסוף הסילסטר. אוקיי. So we stick with the first year and second year, whatever you do, so that is correct. Okay, you get the same result anyway. So just this is for first year, and this is for a little bit more sophisticated. Anyway, what is omega? What? What is omega? What? What is omega? Third. So omega is equal to 1/3. And that means that what? Rho radiation proportional to what? A minus
2, 4.
Right. It's radiation dominated universe.
Both.
So what does it mean? The energy density of radiation, photons, drop down faster than matter. Why is that? Exactly, right? Because of the redshift, right? So as the universe expands, the density goes down, but also their energy goes down. Right? Which means what? Because it goes faster, it drops faster with A. That means that if today raw matter is greater than raw radiation, and A is expanding. A is positive, right? So that means that what? In the past was the opposite. Right? So in the past there was an area in which the energy density in the radiation, photons or relativistic particles, was greater than that of the matter. So the matter-dominated universe, radiation-dominated universe, and they switch. Right?
Do we assume that it's A minus infinity A?
I don't assume anything.
But A could start from 1 in the beginning of the because it doesn't have to be.
Wait, no. One step at a time. One step at a time. Is that all? No. What else can we have in the universe?
Dark matter.
Well, it's dark energy, right? Cosmological constant. Dark matter acts like matter, it's just dark, we just don't see it. Dark matter we refer to matter. When we say raw matter, this is both regular matter, what's called baryonic matter, and dark matter, matter that we don't see. What about sorry? It's the same. It's too hot anyway, so they will become unexpanded. Fermionic will become relevant when you talk about temperatures which are very low. Here anyway, everything's hot. So the last thing we have is the vacuum. 3 is the vacuum energy. What do we mean by vacuum energy? So remember we had G mu nu was 8 pi G T mu nu. And then we added the cosmological constant, so minus lambda G mu nu. Right? Remember that? So instead of writing it like that, I can say T mu nu vacuum I define to be minus lambda over 8 pi G mu nu. Then I can write down G mu nu is 8 pi G T mu nu plus T mu nu vacuum. Just a mathematical manipulation that I'm doing here. So if this is the vacuum, T mu nu of the vacuum, right? Remember T mu nu, right? Rho P P P. What's the relation between rho and P here? Just rho and P from here. From here. Just put the G mu nu. Right?
It's 1 over A squared.
It's just a minus and a plus, right? Just be a rho is equal minus P is equal to lambda over 8 pi G. You didn't use, don't need it. I already put the G.
On T's diagonal, it's all the same.
Yeah.
The metric is not all the same.
No, it is because it's put in the, look at the definition of TV. So what is omega? Right. Now there is nothing like that that you can see in normal life. It's completely counterintuitive. So what does it mean about the change of energy, rho lambda? Constant, right? A to the 0. That's called a vacuum-dominated universe. Which means that sooner or later, that's always going to win.
We assume that A is increasing.
Yeah, A is increasing. You don't have to assume it, it's increasing. Right? So sooner or later, it's going to win. In fact, it already won. It started. Right? But this is completely counterintuitive. So what does it mean? The more vacuum we have, the more energy there is. So as the universe expands, right? As the universe expands, more energy is getting into it. Just completely counterintuitive, right? when we spoke about matter radiation, you could understand the universe expands, density goes down, so the energy density goes down. Here it's exactly the opposite. As the universe expands, we have more vacuum, there is more nothing, and so there is more energy. Which means what? The universe will accelerate, expand even more, because there is more energy in the universe, which is completely counterintuitive. Okay? I mean, you understand that, let's say that there's something starts to expand, but then we have matter, so the matter will try to pull it back by gravity. This is the opposite. Okay, we already ran out of time. Any last questions for now? Yeah.
Find Q.
Yes, we will. So far, I don't think there is anything that I defined Q that we did not use. And it's going to stay that. We're going to use everything that is defined. If you want, I can tell you right now. One of the great questions that we have is how do we measure distances? How do we know the distance to something? That's going to turn out to be crucial. But we'll discuss that not now, we'll discuss that maybe on Thursday, and if we will finish, then on next week. We still have 2 weeks, 3 more lectures. The only thing that I'm concerned, I think there's no problem, we'll finish all of it to tell you about this all in time. And we may have like an extra 1.5 lectures, and then we'll discuss other things. The most logical thing to do is discuss gravitational waves, because this is something which is considered to be basic enough to be in this course. There are other things which are normally being taught in more advanced courses, which we can talk about them as well. The problem is that we won't have enough time to cover gravitational waves properly. But I think you don't really need that. I could give it to you, and then I'll just post it in lecture notes.
For a minute or two, or I don't know. Because in the class, when I came earlier,
You want to see if someone is out.
oh, anyway, it's fine. If they have to come, they will. We cannot force anybody to come. Or okay. It's still recording. That means it will record. Okay.
It's coming.
Ah, okay. So we, from general relativity, we switch to classical mechanics. It's very easy topic. I think some of the people may have already seen it. And this lecture notes is quite elaborate, but still it doesn't have gyroscopic motion. So there are only very few things which have been included in this, and other things which are not included. Okay, anyway it's written, but I'll still tell you where is it taken from. Reference, classical mechanics by I think it's chapter 5. This is the main place where the lecture notes is taken from. There are some parts also taken from Richard Fitzpatrick, but if you can understand, this is quite not very much difficult to understand, but this is a graduate level text, so you might find it a little difficult to understand, but it's not that difficult anyway. Okay, so let's start. What is a rigid body? What is a rigid body? What is a rigid body? Okay.
Body many particles that are connected and not moving relative to each other.
Okay, that's very good. So a rigid body is can be, in simple sense, it can be thought of as a body made up of several number of particles, and the location of particle are fixed with related to each other. So they are not moving. Okay? That's what we call rigid body. And okay, when there are some things which I need to tell, so I will just read them. So how do we define what is precession? What is precession? Like
The axis of rotation is also rotating.
okay, yeah. So like when I have a rigid body where the particles which are located at a particular distance from each other, the body is for some reason, because of some gravitational force or some other reason, if the body is rotating, and along with the rotation of body, the axis along which the body is rotating is also rotating. That's what we call as a precession of the body. And precession can be it can be free precession, like when there is no external force applying on the object, like we can consider, what would it be? Like torque free precession, yeah. And the second would be the precession of like Earth, where it is precession because of the due to the gravitational pull of Earth, Sun and Moon. So when there is no torque acting, it is a free precession. The torque is 0. And when there is a torque acting due to the relative motion of the Earth with the Sun and Moon, that's we call precession due to the presence of an external gravitational force. And in astronomy, we study two types of precession, mostly the axial precession and epicidal precession. Axial precession is the precession of Earth, we can say. That axial precession is also called as a precession of equinox, or namely the rotation axis of Earth. I don't have mean to show the precession, otherwise I can show that when it's very easy to visualize. The Earth is rotating along its own axis, and it is also rotating along the axis so that it makes a cone. I somehow cannot draw because I'm not good at drawing, so this is, okay, I'll try to draw what I have in here. Unfortunately, I do have to. So I have a rigid body, let's say it's Earth, and this is axis of rotation. Consider that this is body rotating. Okay. So what I am showing in here is let's say any solid body. This is the axis of rotation. The body is rotating.
And this happens when, even if the Earth.
No, I'm just showing what is precession in here.
Okay.
What I'm showing from in here, like let's consider we have Earth. So this is the axis of rotation. Along with the axis of rotation, this is that axis, and this axis is also rotating, so it forms a kind of a conical structure. That's what I have to show in here. There's nothing very fancy.
And the Earth is precessing.
Earth is precession.
Why? Because of torque?
Yes, because of the torque from the Sun and the Moon.
Okay.
I mean,
But
there are other kinds of torques as well.
Without the Sun and the Moon, if the Earth was the only object in the universe and rotating.
Yes. No,
There
but
will be no
that
torque.
also it also depends upon the shape of the body. If it is like perfectly symmetric, it won't.
Okay, so
Because of Earth having a little bit of oblate shape, I would say, there is a torque acting on it, and that's how it starts precessing. If the body is like a perfect sphere, then it won't.
okay.
Okay. So there is an axial precession, apsidal precession. Apsidal precession is the one in which the planets and like planet Earth and other moons revolves around the sun, or their own the gravitating body around which they are rotating, like moon is rotating around the Earth and the entire system is rotating around the sun. Okay, so before describing all sorts of precision, what is apsidal precision and stuff, we'll try to build up what is moment of inertia tensor. I hope I do not need to tell what is moment of inertia. No, I don't. That is high school stuff.
No.
Moment of inertia? No, I'm not saying moment of inertia tensor.
No.
Moment of inertia, it was in high school, right?
Yes, of course.
Moment of inertia was there in high school.
גם מה שאתה עושה בתיכון עברו כמה שנים.
אתה צודק. He's right. I used to go to high school hundreds of years ago.
Oh, of course, but still. Then
לא
I don't know.
המעגלית, you learn circular motion. That's the highest.
Okay, what? Okay, fine. Moment of inertia, they're used, I mean, at least the one which I studied, I did not study it here, so the chapter in the circular motion or the rotational motion, when you study, you have the definition of what is inertia, what is moment of inertia. Okay, maybe, forget about it. If it was not there, then.
We learned it in first year, kind
Okay. First year mechanics was taught by Asaf. Okay, good. Then tensor. Because I'm not going to tell what moment of inertia is. I'm going to derive what is moment of inertia tensor. So it's a very basic stuff. You all have seen all those things. I'm just going to make it more visible to your eyes because it was like a long time ago. Maybe at least 2 years ago for someone. Okay, so let's say we have a rigid body made up of n number of particles and the distance between all the particles are fixed. Okay, so a rigid body made up of n number of particles. Again, note, this is R. This, what I mean by in here is like when I write something like this, don't consider this as a V. This is R and this is X. This should never be considered as N. This is X. That's why this is my notation in the sense that's how I write, so don't be confused ever. Okay. Of masses MI. Oh, one more thing that I forgot to mention, like I saw 1 or 2 people's homeworks where they have submitted only 2 or 3 questions and do not submit the remaining one. So that's not, I mean, how I realized is like they submitted at 11:59 something. So if you do not have the time to solve beforehand or you think that it is going to get late, you should tell me beforehand that I won't be able to submit it. I'll submit it maybe next day. It's not like don't submit only 3 questions because you are losing your marks. And I mean, if you don't want marks, I'm happy. I don't have anything problem. But if you think that you need marks and you cannot submit all the problems during that time, tell me, I can extend you the date for 1 more date and then you can submit it. Okay. I is 1, 2, n. Okay. Rigid body made up of a number of particles of masses mi, where I is anything from 1 to n. And then we'll write down the angular momentum vector of the system. Should I? I don't want to write so many words. So the L of rigid body rotating around an axis with one fixed point. L is so 1, 2, and cross This is fine. Angular momentum L mr omega square mr v is r omega, all first year mechanics, hopefully. Yeah. Okay. What is r? R is the radius vector of the ith particle from the chosen starting point where I am willing to measure my r. So like this is the center point where I decide this is my center of mass and I am measuring the distances from there. So this Ri is the distance from that particular point to those particular masses m1, m2, m3 and so on. Okay. And now since Ri is fixed, we are talking about the rigid body. So we can write that, okay, and velocity is entirely due to the rotational motion, and we know that Vi is equals to, everything is vector, yeah, Ri vector cross omega vector, okay, but we know, fine, what I'm going to do is to put this in here. L equals to is from 1 to n mi ri cross omega. Okay. It's fine. What I can do in here, A cross B cross C. I can use it, right? And what is it? I mean,
A dot B times C.
If I am right, let me just check it out. I'm right? Okay, good. All is, everywhere it is vector. When I was undergrad, we used to remember it as a back cab rule. So it's back cab, just written in the reverse way, but okay, that was my way of remembering. You can remember it anyway, or you may not need to remember it as well. Okay, let's put it in here and then see what we get. I is from 1 to n, mi r, oops, okay, square omega minus ri dot omega into r. Okay, fine. It's going to be very easy stuff that you already know all these things, but I don't know how have you never heard of what is precession. So okay, it's then Okay, so this is the angular momentum of a rigid body rotating around a fixed point, where we use the simple formula, simple rotational motion of the velocity, v is r omega, and this thing. What I want to do now is just let's write down this angular momentum in the individual form of the, like, in each component form instead of writing in the summation form. Okay, I'll just remove the summations and write down only x component. Okay, so we have Lx equals to omega x mi ri square minus omega x mi, oops, I xi square minus omega y my xi yi minus zi omega c mi xi zi. Okay. Everybody happy with this one? This is just each and every component of L along X with summation removed, so all the components are written individually. Okay? What I can do is to write these two at this omega x mi ri square minus xi square. This will remains the same, xi yi minus z. There are so many problems with my writing. So this is not 2, this is z. I realize when I write on the blackboard, whiteboard. This is very bad. Okay. And we can denote that. Okay, so from this, what we note here is that each component of angular momentum, if you see, is a linear combination of the angular velocity omega. Okay, it is the function of omega everywhere, right? The linear combination of omega x, omega y, and omega z. And this enables us to write the angular momentum L as I times omega. In Asaf's lecture notes, he has written I with 2 bar, which I don't feel very happy with writing with 2 bars, so I write it this way. Okay. I think I still have to find it a little well. Okay. That means if you look at this L, I can write L as, here I am writing the x component only. That means my angular momentum is a symmetric 3×3 matrix. Okay, and I can write it as Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz multiplied by P. Okay. Now, since we already have this x component of angular momentum, what I'll try to do is to write down each individual, not all of them, but some of the inertia tensors that we get. So right from this equation itself, I can write the 3 inertia moment of inertia tensor components.
Excuse me, did you say that I was symmetric?
Yes. Yes. In 3D, it is symmetric.
Can you show, for example, the L, Y? Just
Yeah. So
show
this
the
is
X.
that's what I was about to write. So
Oh.
this component is, if I'm not mistaken, this is IXX without omega.
Yeah.
Without omega. This is only up to here. This
Can
is
you show
I.
the IYX.
Okay, let me. This is
That's
the.
the IXY.
This is IXY.
Can you show the IYX?
That
The same.
that would be the same.
It must be the same.
That would be the same. Yeah.
Yeah. Okay.
That would exactly be the same. So this is IXY, and this is IXZ, right? Yes. So omega is not the part of IXY. Okay. And there is another nice way of writing it would be, since we know that, okay, let's write it down somewhere here. So IXX would be, write it down in the summation form. I is from 1 to n, mi ri minus xi, both are squares. Okay, and what is this in here is I is from 1 to n, mi yi plus zi square. And the another fancy way of writing it would be, since we know that m is equals to rho into v, I can write this as integral of rho as radial function of r. Yes, rho as y square plus z square. Okay, this is same as this one, written in the integral form. Okay, similarly I can write the ix I y, write it a little below, and I y is mi psi square plus zi square, which is equals 1 to n mi. Oh no, this is already this one, which I can also write as rho of r into x square plus z square dv. Similarly, we can write xy is the same as yx, xz is same as zx, and so on. Okay? Good. My integral sign looks very nice. Okay. Very easy. Now we'll see axis of rotation. Okay. Now we have all these things. Fine. Let's discuss about what is the principal axis of the rotation. So we already saw that our moment of inertia, it depends upon the rotation axis, along which axis the rotation is taking place. And this tensor, as I already told that this is a in 3D, this is a 3 by 3 symmetric matrix. Okay. Therefore, we can define the eigenvalue. And how many eigenvalue will be there? Okay. So 3 by 3 matrix, it has 3 eigenvalues. Let lambda I be the, sometimes it happens like mind writes, means mind understands so fast, but when means the hand is so slow in writing, so it just makes everything, I think of something like 3 words ahead and what I'm writing is 3 words before. Let lambda I be the eigenvalue and omega I be the corresponding eigenvectors. Then I can write it as omega I is equals to lambda I omega I. Happy? Okay. And there are some things that are important to note in here is that the 3 unit vectors, those omega i's, are orthogonal to each other. Okay, and these unit vectors are what we call as a principal axis of rotation of the rigid body. Okay, and when the rigid body rotates along one of these axes, the angular momentum vector L becomes parallel to the angular velocity. Try to think it a bit. When the body rotates along one of these axes, like omega, then the angular momentum becomes parallel to the angular velocity vector omega. So we can, okay, so from this we can decide a coordinate, means we can decide the coordinate axis which coincide with the principal axis. Okay, since we already have this, what we are going to do is to decide a coordinate axis which coincide with one of the principal axis of the rotation.
I also want to mention that the axis of rotations are orthogonal because the matrix is symmetric.
Yes. Yes. Okay. Yeah, that also is there. Okay. So what we are going to do is to, should I write here? We orient our coordinate axis to coincide with one of the principal axes. Let's say, those principal axes would be Ex, Ey, Ez if I define them like this. So let's say the unit vectors along principal axis Ex is prime, Ey, Ez. Okay. And what are the eigenvalues? Like if you look at the moment of inertia tensor, what are those 3 eigenvalues? The diagonals, right? Ixx, Ixy, yeah. So the eigenvalues are Ixx, Iy, Izz. And these are called as I will write it here because principal moment of inertia because they are associated with the principal axis of rotation. Okay, they are also called principal. So I don't think I need to show, but I'll still write. So my I would be I, yeah, I twiddle for the everything in here. Is 0. And if you notice one thing in here, that the principal moments of inertia can never be negative. Look at all the components of moment of inertia, it will never be a negative sign in here. That's why it's like the excess component. Look at the y component, if I have somewhere that is positive, it will not be negative. Okay. I'm doing very bad with time. Okay. Okay. Equation of motion of a rigid body which we also call Euler's equation. Oh, by the way, this is E, not epsilon. Okay. So when I apply a torque to a rigid body, it will start rotating. Okay. And what does torque do? It changes the angular momentum of it. So I can write it that as for an inertial observer. This is an importance. For an inertial observer, the equation of motion is equation motion, and T, capital T, is dl over dt. Okay. Now we would what we want in here is to make the use of those principal axis of rotation, and yes, and okay, so we will decide a coordinate system where we will align our axis of rotation along with one of the principal axis. Okay, the rotation of the rigid body, we will decide a coordinate system like the one we have in here, where the rotation is along one of the principal axis of rotation. Okay, so we already know L is I omega, and okay, fine, and L would be Lx. So here I am denoting it in the prime coordinate, okay, which I will tell right now. Okay, once I will write it down. So it is, what am I doing in here? Oh no. Omega x prime I y I prime omega y prime I z z, right? Yes, omega z prime. Okay, we chose only one of the principal axis of rotation. Fine. Now what are we going to denote is the torque in this equation form, which I will tell you why is it written like this. Coordinates which rotate with the rigid body, we denote it by the prime coordinates. Here the prime coordinate is for the frame in which co-rotates with the rigid body itself. So this is here IN represents the inertial, and this ROT represents the rotation, like the co-rotating angular momentum, and this additional term, this is omega. Okay. Yes. Okay. Here it's written as well. We use the dl over dt prime to denote the derivative of angular momentum in co-rotating frame, one which is rotating with the rigid body. Okay. And this is the inertial observer which I am looking at it. Then comes the part where I will only write down the components of this equation along x, y, and z. Tx prime. If somebody is unhappy, you can tell me. Omega x prime minus I y prime minus I z prime omega. Oops, oh, I forgot to mention one thing. Do I? No, it's okay. Y prime omega z prime is the same thing as, just take the, no, nothing. It's the same as this one. Is there any problem with that? Take this, put here, get this. Okay, along the x component only. So this is only for x component. Similarly, there will be y component and z component as well. So the y component will be ty prime is I y prime omega y prime dot minus I z, right? Prime z prime minus I x prime x prime. Similarly, t z prime would be I prime z prime omega z prime dot minus I y x prime minus I y prime omega x y. This is a very simple thing. It's written in the components form, and these are the Euler's equation of motion for a rigid body. Very bad handwriting. Still. Okay. I did nothing innovative in here. Just I know that if I apply a torque, there will be change in angular momentum, which will cause the rigid body to rotate. I just wrote the each components and put in there and get the torque component. These are the three equations of. These are the three Euler's equations. These are the. This is one of the equation. All the three components of this equation are written. Now we'll discuss about what is precession. We use all these things and then we'll study about the free precession. Okay. Okay. So what do we mean by free precession? Simply put the external torque to 0. There's no external torque applied, and let's see how is the body precession. Okay. So no external torque. Applied. Okay. Now to make our problem simplified, what we'll do is to consider that the axis of rotation is along the z-axis. Okay, so assume that the body has rotational symmetry. Assume rotational symmetry along z. Actually z prime, because we are here everything we are writing in prime. So the consequences of this is, and which we will denote it as something I parallel perpendicular, and I z as I parallel. Okay. For rotational symmetry, spelling of along is quite nice. Okay. So we consider the rotational symmetry along the z-axis. Therefore, we have the moment of inertia along x and y is the same. We denote it some random value. We just say it as I perpendicular and I z as I parallel. That's the way of just denoting what it is.
And the object is rotating around z.
Object is rotating along z. Yes. Okay. So what we are going to do is to write down this equation with torque equals 0. Same equation from there. I can write it there. Okay, so these three equations. I will write down I perpendicular d omega x prime, x prime over dt prime plus I parallel minus I perpendicular omega z prime omega y prime. Is it the same thing? That same thing I have written in here. This is perpendicular component. Omega x prime is the same. Here is the derivative. That's why I put the dot there. I take this thing and it's the same. Okay.
But
Now,
if the rotation is around z, that omega y and omega x are 0, right?
no, why would they be 0?
If rotation is around the z-axis, then omega vector equals.
Oh, no. So, okay, here we are not really saying that the rotation is along the z-axis. We just so that we just say that the rotational. We just use the fact that the rotational symmetry. Yeah, exactly. Rotational symmetry along z-axis. Yeah. Okay. And then we'll write down the ty prime. So this is I perpendicular d omega y prime over dt prime minus I parallel minus I perpendicular omega z prime omega x prime equals 0. You might have problem with this equation. Just look at it, and then the second equation, do you feel happy about it? I think everything is the same. There's nothing wrong in it. Okay? Do I need to explain what? It's the same thing in here. Oops, I did not erase it. Okay. These two are same. So this component goes to 0. This whole thing is 0. I only have that one there. Okay, so from this one, what do we understand from this third equation? That the omega z is the constant of motion. This implies that omega z is the constant of motion. Okay. If things are not fine, you can tell me that you don't understand something instead of just staying quiet. Plus omega, oh my god, nice. Omega y prime equals 0, d omega y prime over dt prime plus, no, it's minus, omega s prime. I use something in here which I will write it now. So what is omega in here? That is, I have not defined what is omega. And omega is I parallel minus I perpendicular divided by I perpendicular into omega z prime. Now you should be happy with this equation. Just put this same thing in here, you get this one. Okay? Good. So what is the solution of these two equations? These are very simple equation. What are the solution of these two equations? So I can just write omega x prime as a cosine of theta. I mean theta in the sense here omega t. And omega y prime as b or something. Okay, same constant. Sine of omega t. Solution. Is okay? Okay. So from this, what we can say that the magnitude of omega x prime ex prime plus omega y prime ey prime is constant. Why is it constant? Yes. Yeah. Good. Okay.
But we're solving for the same A, like is an a factor of omega?
No. Oh, so you want an additional factor in here?
Never mind.
Ah, okay. Now this equation we are somehow going to try to apply to Earth. So this is what we are trying to derive, and now we are going to physically understand what is going on. Okay, so what we are going to consider as, let's consider Earth as a free body precession. There is no torque acting on Earth, although there are torques acting on Earth, okay, because of the moon, sun, and there are other things as well, okay. So we will use this equation and apply it to the rotation of Earth, considering all the external torques are negligible or they are not there, okay. I somehow did not draw the precession. Anyway, you do understand what precession is. Okay. Earth is symmetric about the polar axis. Okay. Right. And what we know that the ratio of this value for the Earth is, okay, I'll just write it down. 1/306, which is equivalent to 0.00327. There is an additional derivation to this as well, where you did try to derive what is the omega, what is the time period of rotation of the Earth. So that's how you know that if you use this formula of omega as omega is omega c prime, this is capital omega, right? 306. From this we predict that the precession of Earth should be 306 or 305 days, which is not the case. Precession of the Earth is 305 days, which does not seem good, right? It's a 365 days, because we excluded all sorts of torque acting on the.
So this should be the precession of the Earth if it's standing in fact in empty space.
In empty space, there is nothing going on. Yes, that's why we have free precession. There's no external torque acting on it, just rotating. This predicts that the Earth should precess once in 306 days. Practically, there are the other complicated things as well, such as the rotation. Actually, Earth moves in little wobbling. There is kind of a wobbling motion as well. So nothing of these things are included in here. So this is the derivation of the free precession, where we exclude all the torque and try to derive for the Earth itself what is the time period of rotation. Fine. I think I am very close to finish time, because if I speak any more, this thing won't record. So yeah, so there are other terms also written. The wobbling include the motion of the atmosphere, current and flow within the core of the Earth, including earthquakes, because anywhere there is not exactly a rigid body also. There are so many things going on below the surface of Earth, on the surface, above the surface of Earth. And this wobbling motion is also called like Chandler's wobble, if people have. Chandler wobble. This is it for today. So next time what we are going to do is the precession of the satellite orbit, where we'll not consider the free precession. Instead, will apply the torque. We'll consider the same motion of the Earth. We'll derive a little bit complicated form of the potential, and from there the Eulerian angles, and then we can go on deriving the omega time period. So basically, precession is this. This should have been included in first year, second year, third year, whichever year, classical mechanics. Okay.
Is this also classical precession of the perihelion? Or?
The classical, yeah. So that we can derive directly from the Kepler's laws. Perihelion of Mercury.
So the orbit of planets is not a perfect ellipse.
It's not. I mean, yes, it is an ellipse. It is not perfect. It's not perfect. What you call sphere, like circular rotation. It is a elliptical rotation.
But so the perihelion is shifting or not?
For all the, but those effects are very negligible for the larger orbits, because the one we see is for mostly for the Mercury. For Mercury.
For man. Okay. But I thought that there was a expected perihelion precession classically, and a minor adjustment from general
relativity. Yes.
So where does the original perihelion precession come from?
Like the
from other planets or from Kepler law? The Keplerian laws dictate a perfect ellipse without
yes.
precession.
If I'm not wrong, yes. Maybe I might be, because I checked it like long time ago, so I need to verify that. Okay. Oh wow, we are still live. So should we continue? No, I think I was told to finish it by once. Okay, anything else? Watch in front of me shows 13.1. I don't know. 13.1.
Extra recording.
Okay. Fine. Anything else?
So, if it's not from Kepler's law, where does the deviation come from? The endgame.
This one in here. What
This is precession of a rotating body in itself.
Yes.
When it rotates not around the.
No, that's why it's a free precession. There is nothing
But if you
applied to
if
it.
treats Earth not as a
Rigid body.
not as a rigid body, just as a point. Okay, no internal angular momentum, just a point, and it's rotating around. I mean, I'm trying to figure out if Einstein a correction for the Mercury perihelion shift is correcting a zero thing or correcting a huge thing with a small thing. Is
I
there?
think it was there in Assam selection also, right?
Sorry.
Did it teach precision of perihelion of Mercury?
He talked about it as a proof for general relativity. I
Or
don't
he
think
did not derive the exact.
I'm not sure.
Okay, I don't know. I'm asking. That's why. Okay, but you can read it. I don't know. You will find in almost all of the general relativity textbooks.
It's okay.
It's there derived actually. How much is the precession C?
It's okay.
Anything further? Nothing? Okay.
Thank you.
So, good. Do I need
I want to show you a trick
For
trick.
for what?
This is a rigid body, right?
Okay. Yes.
Where are the axis of rotation that